those of you who aren't new, welcome back. Welcome back. So for today's video, I've got some finger tracing, some graphs for you. We're gonna go over some graphs in polar coordinates, or using polar coordinates. And we're going to discuss a few different types of those graphs. So we're going to do lots of finger tracing today. Before we get started today, though, I want to let everybody know that my merch is officially out. It is officially out. I am wearing the short sleeve t-shirt right now. I got it in a size large, and it's a little bit bigger on me than I thought, but that's okay. So you can see we've got my logo right in front, and then for the short sleeve t-shirts, the back of it is like, you can see it's got my face on it. So there you go for that one. The long sleeve t-shirts don't have my face on it, and neither do the hoodies. They just have the logo in the front. So if you want one of those instead, that's cool. Unless you want to see my face all the time, or just have me always on your back about things. But anyway, so it's out. Like I said, there's t-shirts, long sleeve tees, crew necks, hoodies, beanies, a coffee mug, and stickers. 3 different size stickers too, and the clothes all come in various sizes as well. So you can pick out the size that will suit you the best. Anyway, so I'm going to post my link for that down below if you want to check it out. And one more thing. So from December 1st through December 7th, if you have signed up for my December Patreon, the $5 tier, you have a chance to win a piece of free merch. Any merch you want, any size you want. So I'm going to be choosing those on December 7th. I'm going to choose 5 people in my $5 tier to win a free piece of merch. And even if you don't win, you get 2 videos on Patreon that you wouldn't see on YouTube or anywhere else. So I feel like that's a win-win. But if you want to be a part of that, go join my Patreon. It has to be the $5 tier, not the $3 tier, the $5 tier, in order to qualify. And that's really it. That's all you have to do. So I know all my Proton tier people. So yeah. And if you already are a Proton tier, thank you so much. Even if you are in Electron tier as well, thank you so much. I appreciate you guys. But anyway, back to the content of this video. So let's get started. Okay, so polar graphs, or graphing like in polar coordinates, are a little bit different. A little bit different than graphing just like regular, would it be like parametric, I guess, graphs, just like a regular Cartesian graph, XYZ kind of a thing. So instead of X, Y, and Z, we use R, which is the radius of whatever it is, and theta, which is the angle at which it goes. There's also phi, which we could use, or phi, some people call it phi. That's the 3rd coordinate in the system, which makes it kind of like 3-dimensional, but we're not going to get into that. We're just going to use radius and theta, or the angle at which it goes down. So typically, normally when we'd start something like this, I like to think of it as like when we're doing like a unit circle. And for those of you who know what the unit circle is, you'll know what I'm talking about. But if we just have like a regular X, Y graph, we usually start at angle 0, basically, is where theta starts, and the radius is however long you want the circle to be. So with a unit circle, it's a radius of 1 because it's 1 unit. So we usually start here at angle 0, and then it goes counterclockwise all the way down until it comes back around and makes a full circle. So that's what we're talking about when we're using those measurements instead of like x coordinates and y coordinates. We're using radius and angle. Radius and angle. So that being said, there's a lot of cool things that you can do with it. You can also do them with x and y coordinates, but sometimes it's simpler to just use radius and angle. So that's what we're going to do. And that's how I'm going to explain it to you in the equations. So for the first graph tracing, we're going to do something very simple. Before we do anything, let us all just take a breath. Release very slowly, very slowly. I know I started this a little bit more excited than I normally do, but we're just gonna make this a little bit more calming for when we actually get into the graph tracing. Okay, so take a moment and release. Okay, so we're going to start with something that we already kind of covered, which is the circle. So with the circle, we all know what a circle is, but when we're giving it an equation, it's just the measure of the radius, because when a circle is drawn, its radius is the same all the way around. So the unit circle is r equals 1, and it's just 1 all the way around. It doesn't matter the angle. So if r equals 1, when the angle is 90 degrees, still 1. When the angle is 180, still 1. 270, still 1. All the way around to 360, it's still 1. Or if we're going to do it in radians, it would be 0, pi over 2, pi, 3 pi over 2, and 2 pi. No matter what, it's the same all the way around. So the equation would be r equals 1 for the unit circle's case, but we can do a radius bigger than that and have something like r equals 3. So it's 3 units all the way around. It just makes the circle bigger, makes it bigger. So it could be r equals 1, r equals 3, r equals 5,286, r equals 0.5. Could even be smaller. So we're just tracing the circle, circle. Tracing just a circle. And the equation I have is r equals 1. And you'll see it on the graph as well. And there's your circle. Now, what if we go a step further and say r equals theta, r equals the angle, r equals the angle? Well, that would mean when the angle is 0, r is 0, and when the angle is pi over 4, r is pi over 4, or when the angle is pi over 2, r is pi over 2, and so on. You see where I'm going with that? So we start at the center, 0, 0, 0, 0. We start at the origin, and then as one gets bigger, so does the other. So that leads us into a spiral. A spiral leads us into a spiral. And this spiral right here, r equals theta, is what we call Archimedes Spiral. It's what we call Archimedes Spiral. R equals theta. So we start in the middle, and then we work our way out. We can go backwards as well. We can go backwards as well. Go forwards. So like I said, we're moving counterclockwise. So we start at 0 right here, then go to pi over 4, then go to pi over 2, or that would be 45 degrees and 90 degrees. So, and then we go up and around 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 and around. We have the Archimedes spiral, and we can do different things with these as well. So we can add, or not add, but we can multiply theta by something. So say we multiply it by 3, that just makes it go even bigger, around, quicker, 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 quicker. It gets bigger, faster. It amplifies, basically it amplifies the spiral. It amplifies the spiral. Amplifies the spiral into something even bigger, 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 bigger. But right now, for our equation, we have Archimedes spiral, r equals theta. Archimedes spiral, r equals theta, r equals theta, r equals theta, 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 r equals theta, 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 theta. Get bigger and bigger and bigger. Spiral, 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 spiral. Spiral out of control. Don't spiral out of control. Don't spiral out of control. No, this is a controlled spiral. We know exactly where it's going to go because we know the equation for it. We know the equation for it. Alright. Next up, we have what is called a cardioid. A cardioid. And personally, I think it looks like a butt. It looks like a booty. So, this guy, a cardioid, can go either flipped this way or flipped this way. And like I said, it looks like a butt. So the equation we are going to use for this one is r equals 1 plus cosine of theta. 1 plus the cosine of theta. And this particular equation will give us a butt like this. Or I should say we start right here and we go around, make its little cheeky cheeks, and back again. So we start here and go around to its cheeks and all the way back. So we start here, loop around, all the way back again. Start here, go up and around again, and back. Start here. Now we could use sine for this as well, but I just wanted to keep it to cosines, so the cosine 1 plus cosine of theta. And back again, around, over the cheek, 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 and back again. I feel like one of those Disney characters where it's like you're watching Disney Channel and they try to make the ears on Mickey Mouse and it just looks like a butt. So that's kind of what I'm doing here, except it really does look like a butt, so. You can follow my fingers. You can follow my fingers. Pew. 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 Follow the fingers, follow the pattern. And like I said, the equation that I'm using is r equals 1 plus the cosine of theta. R equals 1 plus cosine of theta. And I'll show you exactly what that looks like, because I'm sure my tracing it isn't perfect. Yeah. Tracing it isn't perfect, but that's okay. Nobody's perfect. Alright, let's go on to the next one. Okay, so the next one uses the equation r equals 1 plus 2 times the cosine of theta. And this will give us something kind of similar to what we just did, except instead there's going to be a loop inside. A loop inside the loop. A loop within a loop. A loop within a loop. A loop within a loop. And this, I believe, is called an inner loop. Limation. Anybody who knows how to pronounce that properly, it's got the little French C, like you would say like garçon or something like that. It's got that little C, so limation. Inner loop, limation. So that's what it is, and it looks similar to what we just drew, but it's got a loop inside the loop, 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 and it looks something like this. We go up and around, and then we loop in and go around again and back up. So we go up and around, inward, back out again, and back up to the outside loop. Out, around, just want to make sure that my fingers are within view and I'm not just going like all over, you know what I mean? So it's up and around, loop the loop, loop the loop, and out and back again, out and back again, up, around, loop the loop, loop the loop, loop the loop, and back again, up, around, loop the loop, loop the loop, loop the loop, and back again. And yes, you can do this with a sine problem too, but again, I just am using cosine because I want to. And that is the form that the cosine one would take. So our equation again is r equals 1 plus 2 times the cosine of theta. 1 plus 2 times the cosine of theta. Around, up, around, loop, down, back again, up, around, loop, down, back again, loop, back again, loop, back again, up, loop, back again, up, loop, back again. And I will show you an actual picture of it as well. Because again, I can't accurately portray perfectly what I'm doing, so again, feel like a Disney character. But let's go on to the next one. So this next one looks like an infinity sign. Looks like an infinity sign. An infinity sign, an infinity sign, an infinity sign. Looks like an infinity sign. It actually does have a name. It is called a lemniscate, 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 or lemniscate, lemniscate. And again, it just looks like an infinity loop, And the equation for this would be r squared equals cosine 2 times theta, also known as r equals the square root of the cosine of 2 times theta, the cosine of 2 times theta. So there is what gives you the infinity symbol, And again, the correct term for it would be a lemniscate. That's what we would call them. And the infinity symbol we know has 2 loops on either side. And they just go forever and ever 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 and ever. They go on and 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 on. They go on forever. Forever, forever, and ever, and ever, and ever. They go on forever and ever and ever. But this again is what's called a lemniscate. And the equation for this one is r equals the square root of the cosine of 2 times theta. The cosine of 2 times theta. Alright. So for the next one, we're going to get rid of equation is just going to be r equals the cosine of 2 times theta. R equals the cosine of 2 times theta. R equals the cosine of 2 times theta. And this is what we would call an even loop rose curve, an even loop rose curve, even loop rose curve. So because this guy is the cosine of 2 times theta, that means its even loops are going to be 2 times 2. So we're going to have 4 loops right now. 4 loops shaped in flower petals. The even looped ones, they whatever their number is inside of the cosine along with theta, it's going to be that times 2. So if we had the cosine of 4 times theta in there, if we had the cosine of 4 times theta in there, that would mean that we would have 8 flower petals, 8 flower petals. But this one, we just have 4 because it is the cosine of 2 times theta. So this guy, again, he starts here, he goes around, back to 0, and then jumps up, loops around, back to 0, jumps to the side, loops around, back to 0, jumps down, loops to 0, jumps back to where we started. And again, it is right here. We start here, jump back, jump up and around, jump to the side and around, jump down and around, jump back, jump up and around, jump to the side and around, jump down and around, jump back, loop, 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 1 loop, 2 loop, 3 loop, 4 loop, woo, 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 around, 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 and around and around. We go around, 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 around. And I know for sure that I am not doing this right as far as like giving you a correct hand drawing, finger tracing of this loop. So of course you will see the real one, what it looks like. Up and around and around and around and around and around. Around, around, around. Choo. Yeah, so that kind of does it. At the same time, pew, 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 pew. Yeah, so that is the even loop rose curve, even loop rose curve. And the next one and the last one we're going to show today is the odd loop rose curve. And this one for our video today has the equation r equals cosine of 3 times theta. R equals the cosine of 3 times theta. R equals the cosine of 3 times theta. Now with our odd loop rose petals, the number of curves or the number of loops is just the number that's in the cosine. So 3 is in the cosine this time, so that means there are only 3 petals. Or if we had something like cosine of 5 times theta, then we would have 5 petals, but right now we just have 3. 3 petals. We just have 3 petals, 3 petals, 3 petals. We've got 3 petals to go off of. And this guy is not symmetrical across the vertical axis, I guess I would say. So it looks something like this. So it looks similar to what we just did, except it's got 3 petals now. Pew, 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 pew. 1. It would be 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Again, the equation is r equals the cosine of 3 times theta, and it gives us an odd loop rose curve, 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 odd loop rose curve. We can do it really close. We could do it far away and even more. So could do a follow my finger. These ones are easy because you know where the finger is going to be. Because we know the equations. We know the equations. We know what to go off of. We know what to do. We know what to do. We know what to do. Alright. We are going to end the video right there. I hope that you enjoyed it. I hope you enjoyed it. If you did, please give it a like. Give it a like. Share it. Comment, like, share, subscribe, whatever you want to do. But above all, I'm just glad you enjoyed the video. I'm glad you enjoyed the video. Anyway, I hope that you have a good night. A good night or a good morning. Good morning, morning, or a good day. Whatever time of day you're watching this, I hope you are doing very well. And I'll see you all in my next video, so bye guys.